codes are the same. The thousands of nodes are the same. The advantage is that the Hadoop class solutions come from internet services where you have a large amount of work, but it's mostly independently invoked on each one of the nodes. And the web search situation is a whole lot of independent requests, each doing a small amount of work, coming into a back-end server that is then doing a large amount of work for them. We don't tend to have that in the HPC case. We tend to have a big problem. So the most common way of talking about the difference is that the internet services were a lot of independent things that then wanted to process a large amount of data, where the HPC is a distributed shared memory, tightly lockstep parallel computation. So MapReduce has its huge advantage, in my opinion, as an academic, is that it offers a simple way of dealing with the fault tolerance. The programmer doesn't have to think much about the fault tolerance. They code in a very in a stylized framework, a maps followed by a shuffle stage followed by a reduce phase, and if they can cast their problem into that, then the failure of an individual component automatically causes the re-execution of components, and so it's even simpler for them than checkpoint restart is for the HPC world. But restarting just one component doesn't make sense in HPC. So MapReduce by itself is harder to use in the general HPC applications. The analytics side, on the other hand, fits. And so you've seen some analytics work being done in MapReduce. Although now we're getting fairly sophisticated and we're optimizing like graph-based systems to even more efficient frameworks than MapReduce. But I think MapReduce has appealed to a class of projects where they're looking for new frameworks to help more programmers deal with large amounts of data. And so the new programmers that I get, I run a Hadoop cluster at CMU for science, and because we give them Hadoop and it's relatively easy to learn, you get programmers that have no experience with parallelism, with MapReduce or MPI or anything like that, and they can write code. It's not efficient, it has problems, but they're writing code on big data and it's executing in reasonable amounts of time, and that's the great appeal of the MapReduce.
Tell me a little bit more about that, just in the next maybe 4 or 5 minutes. What are some of the lessons you're learning there? What kind of applications are you running? What are you guys doing there?
A lot of my users, there's some astrophysics and processing of simulation data sets or survey data sets. There's some geoscience. There's quite a bit of machine learning, information retrieval. The machine learning tends to be graph-based, Twitter analysis. You may have seen the NPR article, or it was more than just NPR, where they talked about seeing dialects in Twitter. That was done in part on our machine. Right? And this was deliberate on my part. Set the thing up, start running MapReduce, offer the cycles to whatever scientists in the environment want to use it, and then see what they do. And we noticed that their sophistication as parallel programmers was way below the level that I'm used to in the HPC world. And so the tools but turns out MapReduce is immature, so there aren't that many tools either. So I think that in the analytics world, there's going to be a lot of tool production, a lot of support production, and they're going to work on smaller scales than the biggest HPC. And they're going to work with lower efficiency than the biggest HPC. But the frameworks are going to make it easier for programmers that are less well trained to do that portion. At the file system level, MapReduce is just a programming paradigm. It's a job control language, effectively, and a job scheduler. The file systems are more loosely coupled, they're user level, they're libraries plugged into the applications, much like MPI is libraries plugged into the applications. They do reliability by replication, triplication usually, 3 copies of everything, and they are much more, they repair more slowly. That is, they don't trigger as quickly, and then they repair in the background. These architectures are very interesting to me as a RAID guy from a long way back, because they say higher redundancy and slower reaction time, where we tended to go less redundancy and faster response times in repair. And what I'm looking at is the complexity of the code, and whether or not they've got a less complex code. And I think that for a community system that is going to be inherently inefficient, it does make sense to have more expensive, less reactive, and therefore simpler codes. Now, some of my students, there's a presentation tomorrow by one of my students contrasting PVFS as a representative parallel file system and HDFS as a representative cloud file system on its differences. And effectively, what we out of the box, that there's big performance differences, but we can make them all go away. And the fundamental two things are, one, the reliability model. Almost all HPC is striping without reliability of the file system, a reliability provided by hardware RAID inside. PVFS also had that model where HDFS and Panasas don't. They do RAID effectively at the file system level, and they don't rely on it in the individual components. So we had to fix that. And the other is location. That is, most file systems, decisions are made, jobs are launched, nobody has any idea where the data is, and then they just go and get it from wherever it is. MapReduce has an option that says, tell me where that file is, and then they may launch the job closer to the file. And I think that this topology consideration in file systems design is relatively new and very interesting, and probably will persist into the HPC world.